to it right here. Take number 6 as a warm-up real quick, and go finally measure those 3 angles based off what we talked about yesterday on those angle properties. Those are parallel lines. We're talking about some streets there. Depending on maybe the age of the city, getting into the layout of the city. A lot of cities too have parallel lines, perpendicular lines, streets I should say. All right, should not take you that long then. Let's go down to angle 1. Let's go in order here. Angle 1, somebody, what do you have for angle 1? 65? Okay, now to get to that angle 1, I know we're jumping ship here. 3 would have been the first one you got. But angle 1, we got to jump down. We got to use one of those 5 angles from yesterday. So to get down there, myself, I did 115 and 2. What is that relationship between 115 and 2? They are what from what we reviewed yesterday? I'm sorry? There's same side exteriors, not corresponding. They're same side exteriors. Corresponding would be this right here. Okay? Yeah, same side exteriors are supplementary. So they're adding up to 180, and angle 2 should have been 65. And the reason why you said angle 1 was 65 is we have a pair of verticals. So 165, 2 is 65, and then 3 was 115 because there's my vertical angles. Again, I can't stress that to you enough about verticals and also linear pair being used quite a bit throughout the year. And then those parallel lines, all those other 5 angles are going to start happening quite a bit. Okay. All right, let's run through it one more time. Now, on number 7, what we see here is we get 2 pairs of parallel lines intersecting with one another. So in that case, we've got a bunch of angles happening. And with this particular figure, do your best to ignore that 4th line, because that 4th line is not going to have anything to do with depending on what pair of angles you're talking about. So as we look at 2 and 10, true or false? 2 and 10. 2 and 10 are considered to be correspondings. So go find 2, go find 10, and think about what we mean by correspondings. And as you find 2 and 10, what line has nothing to do with 2 and 10 up there? A, B, C, D. Yeah, B has nothing to do with 2 and 10, does it? It has nothing to do with making it up. 2 and 10 is made up of C, D, and a transversal of A. So as we look at 2 and 10 there, I heard a true off that. They're in that same relative position. I totally agree with that's a true off that. All right, 1 and 8. Go find 1 and 8. We got ourselves what? Same side interiors. Definitely false. What do we have instead? Linear pair, I heard. Again, those linear pairs should be obvious immediates. Okay, they're adjacents, and when you see adjacent and they're linear pairs, or sorry, adjacent making supplementaries, that's a linear pair. 14, 15 are just in general, are just supplementary. 14, 15s, are they supplementary? Yes. Mm-hmm. Yes. True. 14 and 15. The reason why we have some supplementaries happening here is it's involved with A and B. A and B are parallel. And with A, B being parallel, 14, 15 are same side interiors, aren't they? They're in between A and B, making it interior. They're on the same side of transversal D. Same side interiors are supplementary, aren't they? And we don't have to put same side interiors, but that's what we have there. Okay. All right, keep going here. 3 and 14, same side exteriors. 3, go find it. 14. I heard false, I heard true. Okay, this is usually one of the tricky ones. What has nothing to do with 3 and 14? A has nothing to do with it. Do your best to ignore A. So 3 and 14, that basically is what we're looking at, isn't it? So if I redraw that, one more time, true or false? True. So that's the one where A has nothing to do with it. 3 and 14, as I kind of redraw that off to the side. Exterior, same side, that's a true one. So that's where I keep, again, kind of going back to, I don't need to say it because it was that. That's where I keep saying, hide it, redraw that if you need to, because that's one, I have a lot of students thinking that these are interiors because it's between A and B, but does A have anything to do with 3 and 14 in that one? No. So you're pretending A is invisible. It's not even there because A has nothing to do with 3 and 14 in that problem. 3 and 14 are made up, again, what, two lines? CD with the transversal of B. Okay? That's kind of a tricky one. 7 and 2 are supplementary. Go find 7, go find 2. Plus, yeah. 7 and 2 are supplementary. Very much because they are a linear pair. 3 and 2 are supplementary. 3 and 2, go find 3 and 2. Another yes. Again, I highlight those lines, just kind of, again, focus in on those two. We get ourselves another same side interiors, don't we? They're in between A and B, same side of the transversal C. That's another same side interior. 9, 15 are congruents. Very much so, because they are my back-to-backs, and what do we call those? Those should be in the automatic vertical. What do we just say? True. Those are my verticals. Last one, 4 and 11 are supplementary. True, false. Now, at the moment, I don't have a direct relationship between 4 and 11. 4 is out here, 11 is out here. But as we said before, we've seen it now for a couple days, if there's not a direct relationship, one thing you can always do is slide 4 down as a vertical angle, right? Isn't 4 the same thing as 6? Because vertical angles are congruent. And by sliding that down, what can you tell me about the new location of 4? 4 and 11 are what? Supplementary, because we have another same side interior. So these are going to be what? True, correct. So don't forget about that vertical angle game there, okay? That's a big one that we can keep using. Because now that we know that's supplementary here, isn't it still going to be supplementary back in its original position? Okay. All right, let's do this. Let's go down circles now. The rabbit hole of circles. Lord help us. Say a little prayer, guys. Because with circles, there is a ton here. We are not even going to scratch the surface today. There's a ton throughout this year. All right. So we're going to go through and talk a lot of vocabulary here today, and a little bit more tomorrow, and do a little bit of application of this tomorrow. Some of this vocabulary we've obviously know from prior years, and some of this vocabulary I don't know if we've ever talked about it. Okay. So as we see on this circle up to the side, we've got a lot of segments and lines on mine happening out, and each one has a special name happening there. And then we're going to talk about some other parts of a circle. There's a lot going on with circles, okay? And then we're going to kind of shotgun it all throughout the school year through the rest of the topics. So let's just jump into it and see how far we can get today, okay? All right, parts of the circle is what we're going to be looking at. So first thing is, on a circle, we got a circle O happening right here. So the first definition we got here is the definition of a circle. Okay, a set of points equidistant from a given point called the center. So if we were to just walk it around, an equidistant from a given point, that is creating what we call as a circle. Okay, so a circle is a set of equal points from a given point called the center. And in this instance, we're going to call this circle, we name it by the center then, circle O. Nothing really crazy yet. We'll get crazy later. Now, some of these definitions you've heard of, but have you really talked about the definition? I don't know. Segment, somebody. A segment that has, let's think about it, one endpoint on the center and one endpoint on the circle. What's that make? Radius, radius, radius. I keep hearing a little bit of radius. Yeah, that's a radius. Okay, so one point on the center, and then it goes to one point on the circle. That is the radius. That's what that's referring to. So we got ourselves a definition of a radius. If we have more than one radius, we call that radii. R-A-D-I-I. Okay. An example of a radius is a segment. Sorry, yes, it's a segment. So it's always using our segment notation. So somebody, give me a name of a segment up there that's a radius. OA, correct. And OA are, what's another segment up there that's a radius? OB, correct. And I can also flip around that order. Segments and lines you can't flip around the order, it doesn't matter. Rays is the one we can't. All right, those are definitely our two radii up there. Those are the only two radii that are actually up there. How about the next one? A segment that contains the center of a circle and has both endpoints on this circle. That's the diameter, right? So if we extend that radius on to the opposite side of the circle, we create our diameter, like you said. Somebody, give me the name of the diameter. Well, don't use that. There you go. I can, again, a diameter is a segment, and segment's only 2, correct. So just AB, right. A diameter is a segment, and a segment's only 2 points. We can reverse it, VA is fine, but again, it's only 2 points. AB is the only option up there of VA. All right, now after that, those are your basic definitions. After this, I don't know. I don't know if you've seen the rest of this before. You might have heard a few of these words in passing, but that might be about it. All right, first thing is, we talked about a segment. A segment, now we're going to say something about a line. A line that intersects a circle at 2 points. Now before I say it out, can anybody identify the line that intersects the circle at 2 points? Yeah, I'm looking for a line, so I'm looking for 2 arrows that intersects this point, or intersects the circle at 2 points. And line EF appears to be doing that, right? So that's the line I'm referring to. EF, and I can reverse it. EF is the same thing as FE. That's no big deal. All right, that's the new vocab word. Let's see if we've heard that before. We call that a secant. My guess is probably not. So I'm just shaking his head no. Patrick, no. I totally would expect that. Jillian, yeah. I totally would expect that's a no. Okay, so that's what a secant is. Somebody there? Beyonce?
Yes.
Should we answer?
No.
No. We're on our notes, okay? All right, so a secant, that's what that secant is. It's a special type of line that comes in to that circle and intersects it at 2 distinct points and just continues on through that circle, okay? So, a secant today. All right, we're gonna talk about another line. All right, let's see here. Another line in that plane of the circle that intersects the circle, though, in exactly 1 point. I say it's a line. It doesn't necessarily have to be a line. It could be a line. It could be a segment. It could be a ray as well. Okay, it could be a line, a segment, a ray. That intersects it, though, at exactly 1 point on that circle. Is there something up there that's doing it at exactly 1 point?
C.
Right there at C is doing that. Okay, and right up here where it's doing that, all right, and I realize I'm missing a little piece in order for me to name that. So let's go and name it A, B, C, D. Let's go ahead and give me a point up here. Let's call that G. I don't know what happened to that. Okay, that is, we're going to name that. And that's looking like a ray then. So we're going to say that is ray CG. And it doesn't, like I said, have to necessarily be a line. That could be a line, a ray, or a segment. That is what we call a tangent. Okay, that is what we call a tangent. So what a tangent is, it's a line, a segment, array that kind of comes in, just barely touches that circle. It touches that circle at just one point and continues on. You know, you've heard the expression going off on a tangent. So you just kind of come on in, touch that point of that circle, and just continue on. All right, kind of that same kind of expression. You just kind of come in, talk about it, and keep on going. All right. Now, where you intersect that circle at that C that you identified for me, that point C, that is what we call that point C. That is what we call the point of tangency. T-A-N. Anything else to drop there? No. Point of tangency. All right. T-A-N-G-E-N-C-Y. So that's what we call the point of tangency, where that tangent, segment, line, ray, whatever, comes in and just kisses that circle and just moves on. And then the other one, this is the one you might have actually heard of before, a segment whose endpoints are on a circle, but not going through the center. So can somebody at least identify me that one? CD? Okay, so it's definitely it is a segment. Okay, I got a bunch of segments, but whose endpoints are on a circle and not going through the center. Yes, that is definitely CD. We can reverse it, CD or DC, and that is what we call. Now you probably have heard of a chord. Okay, Julian says no. All right, a chord. Besides, no, I'm not talking about music. All right, we're talking about a chord here. A chord is a specific segment. All right, it's a chord that is a segment inside a circle, but it does not go through the center. And actually, a diameter is just a special type of chord. It's a special type of chord that does what? It does go through the center then. Okay, so that's what we got for a chord. All right. So really, the big ones are secant, tangent, and for sounds like several of us, a chord is our new vocab today. Now, the last one, if something has congruent radii, what do we have here? Well, when you have congruent radii, all you need to make a circle is a certain length, and then you can start making circles. So if you have congruent radii, the same radius, what we have then is congruent circles. Okay, so that is actually telling us we have same circles, more than one circle of the same shape, same size. Okay, so if you were going to make a bunch of circles of the same size, just lock in the radius. That's what we mean congruent radii. Okay. All right. So let's do some work here today with some of that vocab and a bunch more vocab. Okay, so here, that tangent. All right, when that tangent swoops on in. Okay, when that tangent swoops on in here, here I got me a tangent line. Line AB is tangent. Okay, when it comes on in, this is point P. Point P is my point of tangency. Now, when it comes on in, what happens here is when it intersects a radius, so I have a radius OP right here. When it intersects a radius, what happens then is it's always going to be perpendicular. Okay? This is going to be the case of whenever it intersects with a radius, okay, that the, I went the letter A, AB, the tangent is going to be perpendicular to the radius, which in this case is OP. So this tangent, that is the one thing I want you to kind of take away today from tangents. Two things. One, it comes in and just kisses that circle at one point, the point of tangency. And then the second thing I want you to start kind of filing away, that we're going to use a lot throughout the school year, is when it intersects that circle and it meets up with the radius, it's always going to be perpendicular. Okay. Now, with that, that's going to lead us into, for us throughout this year, a bunch of Pythagorean theorem again. Pythagorean theorem's about to kind of rear his head again. Okay. All right. Let's flip. Let's keep talking here about circles. Now, we just talked about a bunch of lines and segments and rays. Now what we're going to do is kind of actually talk about the actual part of the circle. We're going to cut up that part of the circle. Now again, we just saw that several of you have not heard about the secant. Actually, several, I don't think all of you have. Many of you haven't heard about the secant or the tangent. And maybe a few of you have a chord. Now this next part, you probably heard the word, but done in a math class, probably not. All right, so now what we're going to talk about is, as I said, the actual, this parts of the circle, around the circle. All right, what I just kind of started highlighting is what we call a part of a circle, is what we call an arc. So we've all heard of the word of an arc, okay? Not A-R-K, but A-R-C. All right, a part of a circle, that's what we're referring to. So part of a circle is what we call an arc. And that is measured, and we're going to see here, it's measured in terms of degrees, okay? And how many degrees of a circle? 360. So as we're going to see here today with arcs are measured as 360 degrees. And there's a relationship happening here, as we've started to also see with polygons too. An angle is a special angle whose vertex is the center of a circle. We call that angle, I've mentioned to you guys already before, a central angle. Okay. So if you have an angle such that the vertex is at the center, we call that angle a central angle. We get really crazy there. So can somebody name me a central angle here? Eva?
COB.
COB. Because O is at the center, right? And naming it, I need 3 points there. And she suggested angle COB. What's another angle at the center? AOB or BOA. We can reverse it as well. That's another central angle, AOB. I keep writing my B's weird. AOB. Okay. So those are what we call, again, central angles, because again, the vertex is at the center, and what we've done here is highlighted what we say is the central angle. Okay. Now, what we also start doing here is we start cutting up this circle into different types of arcs, and there's 3 different types of arcs out there, and they're all in relation to a semicircle. When we say a semicircle, what comes to mind? Half a circle, duh. Okay, a semicircle is half of a circle. So they're all in relation to a semicircle. And our first type of arc is a semicircle. And what does a semicircle measure? Exactly 180 degrees, as Carter said. So let's give an example of a semicircle. So what we're going to be doing here is now naming a new type of thing here. We have not talked about naming arcs. A semicircle is an arc. What we just named a second ago was an angle. Now we're going to name an arc. So we've not named arcs at all until right now. So again, an arc, a semicircle is an arc. And to name arcs, we walk it around. We walk it around the circle. So how do we name a semicircle? Walk it around here. Where do you see a semicircle? AC. I heard somebody say AC. That makes sense. because we walk it around the circle, right? Now, here's the thing though. Whoever said AC, were you referring to this top semicircle? Or which semicircle did you see? Or were you referring to this bottom one? It can't be both. It's got to be one or the other. You're referring to the top one. Okay. So yeah, that's the thing about semicircles. Which one are you referring to? So we're referring to the top one. So try to give me a better name than just AC then. ADC. Right. So when you're referring to a semicircle, we have to use 3 points. Right. Where you start, where you stop, and in between to tell me which direction to go. And what's in between A and C to tell me which direction to go? Right. ADC is that semicircle. Now, how do I know it's a semicircle? Sorry, how do I know it's an arc we're talking about? We're going to use the arc symbol. That's my arc symbol. It's the new one for today. Okay. Exactly it. We're going to name a semicircle where you start and stop, but you got to tell me a direction to go. And you all, not all, but you told me you were talking about the top one. So you're going to tell me point D. What if you're referring to the bottom one? ABC, correct. The bottom one is named as ABC. That is correct. Now you can reverse the order. CDA is fine as well, or CBA as well. Start and stop, but in the middle's got to be the direction to go. Okay? All right. Those are semicircles. We're going to do more practice with that. Now, it's all built off a semicircle. It's either more than 180 or less than 180. So if you are smaller than a semicircle, smaller than 180 degrees, okay, we have what we call a minor arc. So a minor arc, it is less than 180. So with that in mind, can somebody give me an example if you think that what a minor arc is? Yanta? All right. So he suggested AD, and that definitely is less than 180. And he reversed it and said DA, and that is absolutely correct. Somebody give me another minor arc, Brianna? AB, yep, that's definitely less than 180. Somebody give me another one. CB, yep. Give me another one. CD, yep, that's another one. There's another one up there. Sam? BD, yep, that's another one. Now, when he said BD, he did not say C in between there, and that's not at all necessary. Because when you're talking about a minor arcs, you take the shortest distance between the two. Minor arcs are only named with 2 points. Okay? So when you say minor arc and you say 2 points, those go together. So when you said BD, we automatically go that shortest route. Don't ever give me 3 points. All right? Minor arcs should be named with 2 points. Now, if you said BCD, it's not necessarily wrong, it's just redundant. Minor arcs are understood 2 points. Okay? All right. We can keep going, but those are all examples of minor arcs. And then if you're above, if you're more than a major arc, a major arc is larger than a semicircle. Okay? So more than 180 degrees. Those are your 3 type of arcs. So with a major arc, somebody think about more than 180. Somebody give me an example of a major arc, you think. Yante. Okay, so give me a second there. You said A, D, C, B, right? All right, that's entirely correct. I'm going to clean it up just a small bit. Take off one of those middles. You only need one of those middles. There you go. So where you start and where you stop, just like a semicircle, but you only need to give me one of those points in between. Because once you tell me AD or AC, I know which direction to go and I continue on that route. So as Iantes cleaned it up, I think he said ACB. That works. You could have also said ADB. It means the same thing. That's an example of a major arc, because ACB, that is definitely more than 180 degrees, right? Carter? All right, give me a second. So that's going to get messy quick. You said BAD. That definitely appears to be more than 180. Yep, BAD. All right. Now, if I just said, go back to Carter's real quick, and if I just said BD, if you just say BD, that is not correct. BD, we always take then the shortest path. BD would be an example of right here, minor arc. So on major arcs, you are using 3 points, just like a semicircle. Okay. Anybody else got me one more major up there? C, B, D, or you could say CAD. Either one's fine. And on all those, just like we keep telling you, you can reverse the direction too. Okay. Sounds great. All right, last one. Last vocab word there. Blank are arcs of the same circle that have exactly 1 point in common. We're going to bring in one of our vocab words from angles. They're sharing something in common. What's one of our vocab words that we've had something where we shared something with angles? So we have also adjacent arcs, which makes sense. We have adjacent arcs up here. Just like adjacent angles, we have adjacent arcs. They're sharing a point in common. So can somebody give me a pair of adjacent arcs up here? DC and CB, because they are sharing point C. DC and CB, that would be just fine, because they are sharing point C. Those are adjacent arcs. They're right next to each other, aren't they? Sharing point C. All right, sounds great. Let's do some work with all that then. Just like we did with angles the last few days and even parallel lines, now we're to naming them out and even maybe finding some measures as well. All right, let's take a moment here. Let's know that vocab. It's a messy picture. Somebody, let's go. I'm gonna want an acute central angle. Let's do this. I'm gonna do this. Give you 2 minutes here. You go take a minute, 2 minutes. Find out, answer these out on your own, and then we'll come back together and we'll pause there. Okay. So, give you a minute or two on your own. Again, it could be more than one answer here. Let's see about being worse. All right. An acute central angle. Let's run through this kind of quickly here. An acute central angle, AOC, I heard? Yep, angle AOC, that definitely works as one answer. Or angle AOD, right? More than one answer. Wait, AOC is not acute. You were back that out. That's obtuse, isn't it? I heard an AOC. I think I just went with it. DOE or COE would have been fine. Let's try that again. EOC would have worked. Maybe that's what I heard, and I just didn't process that. All right. AOC for obtuse central angle or DOE would have been fine. Straight angle.
Wait.
AO. Hold on. Straight angle. It's got to be name angle. Angle AOE. To name that angle, to name that straight angle, I gotta have 3 points. I'm hearing some AC or I can be F. DOC works too. Yep. But I gotta have 3 points to name that angle. And AC would not be enough. It has to be 3 points to name that angle, okay? And DOC works as well. 2 congruent angles. DOC and what? AOE. I could do those 2 straights. Or I could do my verticals. COE. Yep. And AOD. There's my There's my vertical angles in action there. Yep. Okay. Now our new ones. Those are kind of our old ones. Our new ones. Minor arcs that are congruent. A, D, and C. And that's going actually right back to our vertical angles. Okay? We're going to talk about that relationship later. It's not necessarily a crazy relationship, but hopefully you realize those are vertical angles that are congruent. Those arcs are going to turn out to be congruent as well. Minor arcs, but not congruent. C what? CB I heard. And what? AD, sure. Those are not congruent. Give me a semicircle. D, E, C. Yep, that is a semicircle. What was another one I heard? A what? A, D, E. Yep. And there's more than one answer. A major arc that contains point A. A what? A, D, C. Walk it around, trace out. A, D, C. That does sound like a major. It looks like a major. All right, a diameter, there's two options. Diameter is CD or AE, right? A radius, I got 4. OC, OE, OD, or, right. A secant, there's only the one. BF is my secant. Line. BF, secant is a line. So BF. Chord, AC. And chord on that one, AC is 1. And you could actually use that BF again and just drop off the 2 lines of that. And you could actually also say chord BF as well. That could double as a chord as well. AC is the obvious one. And the last one here, a tangent. EG, and on that tangent, looks like they're using a line on that tangent. So I would go with line EG off that, because it appears to be a line. Okay? All right, that's where we will pause things here today.